All right, good afternoon, everyone. Let's get started. So today we are going to start a new chapter about distributed training. So in the first two parts of the lecture, let's first give a quick review. We learn about how to accelerate inference, right? Inference techniques, general purpose techniques, domain-specific techniques, including pruning, quantization, neural architecture search, distillation for large language models, for diffusion models, for video models, etc. So from today, we are going to start a new chapter about training, how to make training faster. If you encounter a model is too slow to train, hopefully we'll teach you some techniques to make your training faster. So this is the agenda for today. We'll start with background and motivation, why we need distributed training, and we'll cover several techniques about parallelization, including data parallelism, model parallelism, pipeline parallelism, sequence parallelism. Model parallelism is also called tensor parallelism. In particular, for data parallelism, we'll talk about several sharding methods like 0, 1, 2, 3, and fully sharded distributed FSDP parallelism, FSDP techniques, okay, fully sharded distributed parallelism, okay, data parallelism. So let's start with background and motivation. So these models are usually coming at a very high cost of training. So the higher the accuracy, the more max we need. Okay, the more max we need. To train this GPT-3 model require 3 million GPU hours, which is too slow to train if you have a single GPU. So we need multiple GPUs to make it faster. So this is showing how long it takes to train a model, like from less than 50 to BERT-based to NLG, GPT-3, particularly for GPT-3, 175 billion parameters, it's a huge amount of GPU hours. If you have a single GPU, that will take 355 years to train the model, which is too slow. And these numbers are measured on NVIDIA A100 GPU. So the boss asks you, what did you do over the last month? And the answer is train the model for 1 epoch. Boss asks, fine, what's the plan for the next month? And answer, train the model for 1 more epoch, right? So that greatly limits the productivity of our designers, those machine learning practitioners, right? So we want to make the model train faster. So we want to use multiple GPUs, just to buy multiple GPUs to do that. For example, if training a task take 10 GPU, a single GPU 10 days, 10 GPU days. If you have 1,024 GPUs, that will take only 14 minutes over just a cup of coffee. So this kind of technique can greatly speed up our research and development cycle. So let's see a real use case that our lab did for distributed training a couple of years ago. So we explored this Summit supercomputer. It has many V100 cores. It's pretty big. At that time, we trained over 1,000 GPUs at that time. Each GPU is V100. That's already 2 or 3 generations ago. V100 and the A100 and the H100, and now B100 is coming. At that time, it has 200 gigabit per second InfiniBand. Now you can easily get 400 gigabit per second. After this was in 2019. This was in 2019. So only 4 years. There's tremendous development, this tremendous improvement from NVIDIA for the GPU family. So this is at that time we trained this video understanding module, temporal shift module for over 660 hours of video, which is considered a small amount these days, but at that time it was considered a pretty big amount. So with only 1 node, 6 GPUs, that take 49 hours, roughly 2 days. And with 128 nodes, that's 700 GPUs, 28 minutes. With 1,536 GPUs, we shortened that to 14 minutes. That's 211 times faster. So theoretically, it should be 256 times faster. Okay, so the accuracy is well maintained. So we've talked about temporal shift module just to shift the channels across different frames to enable temporal modeling, which is a good replacement of 3D convolution that is much more computationally efficient. So this is just showing by utilizing more GPUs by buying more GPUs, so we can shorten the design cycle from 2 days to 14 minutes. Okay, so let's dive deeper into how do we achieve that, given distributed training can be so helpful to shorten the design cycle. Let's see how do we parallelize and how do we exploit so many GPUs. Say you have budget to buy like 1,000 GPUs, how to program them, how to exploit them. So let's talk about parallelization techniques in the following 4 aspects. One is data parallelism, pipeline parallelism, tensor parallelism, and sequence parallelism. So this sequence parallelism is a new content we added this year. In last year and the year before last year, we don't have this content. This is new given the fast development of long sequence, long context, large language model. A video can be an hour long video in 1080p can easily exceed 100 million tokens. Right, a whole series of Harry Potter book is 1 million tokens. So how to parallelize them across the sequence dimension is also very crucial. So we added this new chapter. So let's first look at the data parallelism. Imagine we have a deep learning model. We have a lot of training data. One idea is to distribute across different parts of the data. Right? We have 3 parts, blue part, the green part, the orange part. And then we parallelize the blue part to GPU1, the green part to GPU2, and the orange part to GPU-N. So we are splitting the training data to multiple GPUs, splitting the data. Okay, and each GPU are sharing the same model across different GPUs. So that's data parallelism. We are partitioning the data. We are sharing the model. Okay. And the second technique, we can partition the model and sharing the data. Partition the model in N parts in a pipeline manner, okay? But they are sharing the same training data set, So we have a single copy of data, but we are partitioning, splitting the model, okay? On GPU1, GPU2, GPU-N are processing different layers of the model. And next is the tensor parallelism. We can partition in another dimension. Okay, we are also partitioning the model, but not from the layer dimension, but within the layer, we are partitioning a different part of the matrix multiplication across different GPUs. We are partitioning the activations. The first, the third, next third, the last third of the activation is fed to different GPUs. And in this case, GPU1 is responsible for the first third of the activation. And then we can continue the same way for different layers. Okay, so this is also sharing the same training data, but we are partitioning across different activations for the model. For example, if you have a big matrix multiplication, like 4K by 4K, you can partition that by 4K to 4K by 2K, and use 2 GPUs to process that 4K matrix multiplication. Okay, and lastly, we have this sequence parallelism. Okay, so say we have a long text for training, like 3 books, right? First, we have this batch size dimension, token dimension, hidden dimension. Okay, so the batch dimension, we can use the data parallelism, split by the batch. Like 3 books, we split it and use only train 1 book on 1 GPU. And then from the token dimension, the token is too long. Like the book can have like tens of thousands of tokens. So we can exploit sequence parallelism. A long sequence, we can split it into several shorter sequences. We can split the tokens. Okay? Just like this book may have 3 chapters, we can feed chapter 1 to GPU1, chapter 2 to GPU2, chapter 3 to GPU3, just like this. Okay? So each GPU is responsible for all the entire model. Okay? The model is not, each GPU has the whole model, but it's only responsible for processing part of the sequence. Okay, part of the sequence. Since the total sequence is too long, each GPU just process part of it. So that's sequence parallelism. Okay, so this is a quick overview of the 4 different parallelization approaches. And now we are going to dive deeper into each parallelization approach and see how do we implement them. So we are going to start with the data parallelism, communication primitives, zero, and FSDP. So these are all related to data parallelism. Next, we're going to talk about pipeline parallelism, and then tensor parallelism, followed by sequence parallelism, to cover all the 4 parallelization techniques. Okay, ready? Let's go with the data parallelism. So let's first introduce a method called using a parameter server. Okay, so we can scale the distributed training with parameter server. So this is a centralized approach, not quite widely used anymore. But let me start by introducing the basics. So there is a central controller of the whole training process, and then we have many worker nodes. In this case, we have 4 workers. Okay, the parameter server will receive the gradient from the workers and send back the aggregated results. And each worker will receive part of the training data, splitted training data, and then update the and calculate the gradient and send the gradient to the parameter server. So put it another way, we have a neural net model, we have a gradient in the parameter server, and we have pool of worker node, including the gradient, the local replica of the neural network model, and the training data. And the training data is split from the entire training data set. And we split it into 4 parts. Each GPU is responsible for 1 part. To begin with, the parameter server will replicate the model. And each worker will pull the model from the parameter server. Okay? So 4 workers, each will pull the model from the worker. And then it will also split the data set randomly but evenly across 4 workers. And we have the weight, we have the data, then each worker will calculate the local gradient on that piece of training data over that local replica of the model. So the question is, are the 4 local gradients the same? No, they are not the same because they're using the same model, but they're using different piece of training data, which is randomly splitted. Okay, so they each have a copy of local gradients. What they do is they push the local gradient and sum them up to the parameter server. Okay, so we have the parameter server right here. And the parameter server is responsible for updating the neural network model with the gradient. So now the parameter server will replicate and pull, each worker will replicate and pull the updated model to update its local copy. Otherwise, its local replica will be stale. Okay, now it's going to replicate the new model and then repeat this process to pull the model, split the data, calculate the local gradient, send it to the parameter server update the model, and then each worker pull it again. So if we see the difference between single node training versus distributed training, previously in each iteration, we sample the data, calculate the gradient, perform a step to update the weight. Now we add this part to pull the gradient from the parameter server. And then it's the same, sample the data, calculate the gradient, and we added another part here to push the gradient to the parameter server and sum it up. And then parameter server perform this gradient step. So there are actually 2 synchronization steps here in the red. Okay, so make sure each server each worker is synchronized. So synchronization has overhead. This is not free. So let's talk about these communication primitives and see how can we save this communication overhead. So there are a couple of communication primitives when you come to send and receive data over the network across different nodes. So simplest one is send and receive. Okay, so we have several nodes. We can send from node 0 to node 3. And this is receiving from node 3 to node 0. Okay, so this is one-to-one communication, transferring data from one to another. And then we have one-to-many, scatter and gather. Okay, so scatter basically send a tensor to all the other workers. Okay, so a tensor, 4 components, and it will send it to 0, 1, 2, 3. So this is one-to-many, one-to-many. And gather is basically the reverse, many to one. Okay, we gather the data from worker 0, worker 1, worker 2, worker 3, and I gather everything to worker 0. So receive the tensor from all other workers is called gather. It's many to one versus scatter is sending the data to many servers, one to many. Another one to many is actually reduce. Okay, so reduce is very similar to gather, but it's different. So gather basically only gather all the data, but reduce will do another operation, which is to sum it up, or finding the sum, finding the max. It's going to do a reduce operation after the gather operation. So you can think of reduce operation as the gather operation followed by a reduction operation. So if you sum them up, then that's reduce. If you don't sum it up, leave it as is, then it's gather. There's also another one-to-many operation called broadcast. So broadcast, one tensor to all the workers. Broadcast is actually different from scatter. So scatter is going to send a tensor, different part of the tensor to different workers, and different worker will receive different piece of data. But broadcast will send identical copies of data to all the other workers. So that's the difference between broadcast versus scatter. Finally, we have this many to many operation. So this is all reduce, this is all gather. Okay, so all reduce will perform a reduce operation on all the workers. So if you look at all reduce versus reduce, reduce is basically working on one receiver. But for all reduce, you're performing reduce on all the workers. Reduce on 0, reduce on 1, 2, 3. Okay. And similarly, for the all gather operation is to perform gather on all the workers. Gather on worker 0, gather from worker 1, gather on worker 2, gather on worker 3. So that's the relationship between reduce, gather, all reduce, and all gather. So this is reduce, this is gather, just operating on one receiver, operating on one receiver, but many to many is operating on many receivers. Okay, so they share some similar properties. So let's see, how do we use those communication primitives in the parameter server setting? So we just talk about parameter server, and then we have many workers. They have a different replica of the training data. So which type of communication scheme is used when we are replicating in the blue part versus in the orange part when we are pushing and summing the gradients? So we have all reduce, all gather, reduce, broadcast, scatter, gather, send, and receive. During the orange and blue operation, which communication primitive are we using? Yeah, for the broadcast is used for replicating and pull, right? So we have our central parameter server, and we want to broadcast the weight to all the workers. And for push and sum, it's reduce. And so we're averaging from all the workers. Every worker gets its own gradient, and we want to sum the gradient in the parameter server. So it's actually reduce. It's not only gather, it need to also perform a reduction. So it's reduce. So what is the bottleneck here? What is the bandwidth requirement to do this? For replicate and pool, each worker is O1, right? You just need to pull one copy of data. But for the parameter server, the bandwidth is On because you have N workers. So the replicate and pool will take On communication complexity. For the push, each worker just need to push its own copy of gradient. So that's O1. But for parameter server, they need to receive N copies. So the complexity is On. So it's actually pretty heavy, right? For the parameter server, the networking traffic is On. It's not quite scalable. The more worker you have, the larger the bandwidth requirement is needed. So the bandwidth of the central parameter server will grow linearly with the amount of workers, which can be a bottleneck when you have a lot of machines. So a natural thinking is, can we make it more scalable by getting rid of this centralized parameter server and make everything decentralized without a parameter server? Of course, we can do that by using this all-reduce operation to get rid of this centralized parameter server. And how do we do that? Say we start with a naive all-reduce implementation by using the sequential way. So each GPU will calculate its local gradient on its own piece of data, right? And now we perform all-reduce on all the nodes. Okay, so reduce on node 0, okay, reduce on node 1, reduce on node 2, reduce on node 3. So each node, each worker will do a gather and then reduction to combine all the gradients together. Although the calculation has some redundancy, they're all calculating the sum of this green, yellow, blue, and red, right? So what is the time complexity? Actually, that's On. We're sequentially doing the reduction, okay? So time is On. What about the bandwidth? It's also On because each worker requires receiving the data from all the other workers. So both the time and bandwidth is On, which is not good. So can we do better? So we can do this a better ring reduce operation by using this ring or reduce. What does that look like? So step 1, worker 0 send the gradient to worker 1. Worker 1 send it to worker 2. Worker 2 send it to worker 3. Worker 3 send it to worker 0. Okay. So at this moment, worker 0 has data both from itself and also from worker 3. Okay. So worker 1 can have the data, can have the gradient both from worker 1 and worker 0, since worker 0 is sending to worker 1. And worker 1 previously already have this yellow data. So now it has both the yellow data and the green data. So that's the first step. And the second step, we do the same. Worker 0 send data to worker 1 such that worker 1 has both the green, the yellow, and also the red. Okay, it has red, it has green, it has yellow. And worker 1 send its gradient to worker 2 such that worker 2 will have the orange, the yellow, the blue, and also the green. The green comes from worker 1. Okay, and we do the same for 2 to 3, 3 to 0 in a ring manner. So everyone just sending to its neighbor. And after step 3, 0 send to 1, 1 send to 2, so that worker 1 has data from the red, the green, the yellow, and also the blue. So now it has all the data you need. And similar thing happens for all the other nodes. They each have the green, the orange, the yellow, the blue, and the red. So only in 4 steps, we have all the data. So the time is still O(n). Since we have 4 nodes, we require 3 steps. So time is still O(n), but bandwidth is only O(1). We only need to communicate with our neighbor. So there's no very little bandwidth needed right here. Remember previously, the parameter server, the centralized parameter server require O(n) bandwidth. Now everything is O(1), so that's good. We made some progress by using this ring or reduce. Can we do even better? There is still some redundant computation, right? Can we do even better? Okay, so before looking at the more advanced version, let's look at a naive or reduced implementation, parallel reduce. So previously we talked about sequential or reduce. Have 4 steps for 4 workers. We can do everything in parallel. At the same time, worker 0 is doing a reduce, worker 1, worker 2, worker 3, they are all doing the reduce. Okay, so we only need O(1) time. Since it's not sequential, it's parallel. However, the bandwidth is O(n) squared. So all the each arrow, everything is happening at the same time. So we have n, so we have O(n) squared communication happening in the middle. So the time is pretty short, but the bandwidth is too large. Compared with this ring or reduce, we need the O(n) time. Time is large, but bandwidth is small. So can we have an even better solution? Summarize so far, we talk about parameter server, okay? O(1) time, but peak node bandwidth is O(n), total bandwidth is O(n). Sequential or reduce, time is O(n), peak node bandwidth O(n), total bandwidth is also O(n). For all reduce, using the ring manner, the peak node bandwidth is reduced to O(1), since I only need to communicate with my neighbor. Total bandwidth is still O(n), since I have to do that for n times. And parallel or reduce, time is O(1), which is pretty good. But peak node bandwidth is O(n) for each node. The total bandwidth is O(n) squared. And now we want to combine the advantage of the ring and the parallel or reduce. Ring or reduce combined with parallel or reduce. And let's see how do we further reduce the bandwidth and time. Okay, so now the example gets a little more complicated. So let's use 8 nodes in this example. Okay, so in the first cycle, we will combine the data from adjacent node with neighbors with offset of 1. That's adjacent node. So 1 combined with 2, 2 with 3, 3 with 4, 5 with 6, 7 with 8. And as a result, node 1 has both the green and red. Node 2 also have green and red. Node 3 has this blue and orange, etc. Okay, so just after 1 cycle, everybody communicate with its neighbor with offset 1. Step 2, each node will exchange with neighbors with offset 2. Okay, so node 1 will communicate with node 3. And node 3 will communicate with node 1. Node 2 will communicate with node 4. Okay, so this is one group. And the other group, node 5 will communicate with node 7 and 6 with 8. And as a result, you can see we are already making some progress. Everything on the left, they already have all 4 colors. Everything on the right already has all the 4 colors. So we can do one more iteration to complete this. We can complete this job. So let's brainstorm. How should we do next? What should we communicate in the next step so that everybody has 8 colors? With a larger offset. First one, last one, or first one with the 5th one, right? So if we exchange the node with neighbors of offset 4, then the first node and the fifth node, they will communicate with each other, right? And second one with the sixth one. And as a result, this one will have also this color. So all the 8 colors. For each node, we'll have all the 8 colors, right? And we complete this process. And how many cycles did we take? Actually, we have 8 nodes, but only 3 cycles. Okay, after 3 cycles, every node has the data from everybody else. So only log n steps rather than O(n) step, which is much faster. Right. So this is called recursive halving or reduce. People also call it butterfly or reduce because this structure looks like a butterfly, but not exactly. So just for n workers, or reduce can finish within log n steps. So this is much widely used technique compared with the parameter server. Like in our lab, we do a lot of distributed training, but we don't use a centralized parameter server. Instead, we use this or reduce method. Okay. Okay, so now let's switch gear to continue talk about data parallelism to reduce the memory using the 0, 1, 2, 3 and fully sharded distributed fully sharded data parallelism. Before that, let's take a quick break for 5 minutes. All right, welcome back. Let's continue a discussion about zero and FSDP. So zero is actually a very popular technique for training large language model these days. It stands for zero redundancy optimizer. So let's see how that works. So recently, the large language model is pretty big. Like GPT-3 is 175 billion parameters. If we train it even in FP16, so just to hold those weight, how much memory do we need? We need 350 gigabytes of memory just to hold the weight, not to mention the activations, the gradient, the optimizer state. Well, A100 GPU or H100 GPU has 80 gigabytes of memory. B100 is getting larger, but still less than 200, right? So even the best GPU cannot fit the models weight into memory. So how do we solve that problem using limited GPU memory to train big model? So let's first break down what is the memory consumption to train a single parameter. Okay, so we can break down into 3 components: the weight, 2 bytes per weight, assuming it's FP16 training, which is already pretty popular these days. And gradient, 2 bytes, FP16. We also have to store those optimizer states, including 3 parts. One is a FP32 copy of the parameter. So the weight requires a master copy, a full precision master copy for the accumulation. So that's 4 bytes. We need another two numbers for the optimizer state. If you need to use the item optimizer, you need to store both the first order and second order momentum. The 2 momentum require 2 numbers, and the master copy of the weight is another number. So altogether, we need 3 numbers. Every number is 4 bytes. So we need altogether 12 bytes for the optimizer states. Okay, so this is the optimizer state. This is the gradient. This is the weight. Okay, so optimizer state actually occupies a pretty large portion of the total memory. So this is the total sum, summing up the weight, the gradient, optimizer state. Altogether, you need 16 bytes to store to train for each parameter. Okay, so we can calculate if we do the training naively, how many parameter can you train on a 80 gigabyte of memory, even not to mention the activation. So 16 bytes for each parameter. We can train only 5 billion parameter model, not not even a Llama 2 7B. Okay, so only 5 billion parameters, which is far away from the current state of the art. So how can we do better? So previously, we are having n copies of the weight gradient of the optimizer state across each GPU. Since we are doing data parallelism, they are processing different data, splitting the data, but they are sharing the model. So each GPU has the same copy. 0.1 basically propose we can partition, or we can call it shard, the optimizer state. So since we have n GPUs, we don't need to store we can only store the local copy for each of them, rather than storing n copies of them. So if we have n GPUs, we no longer need to store 12 bytes each, but we can store 12 divided by n. So we are sharding the optimizer state. If we have n equal to 64, we put n equal to 64 right here. Each parameter requires only 4.2 bytes, and we can fit 19 bytes, 19 billion parameter in a single 80 gigabyte of GPU. So that's 0.1. 0.2 is more aggressive. Okay. 0 stands for zero redundancy optimizer. So 0.2 also shard not only the optimizer states, but also the gradient. Okay. So the gradient is also 2 divided by n. Shard the gradient as well. So each parameter requires 2.2 bytes to train, and 80 gigabyte of memory can train a 36 billion parameter model. So that's much bigger. So that's already pretty big. 0.3 is an even more aggressive approach by sharding not only the optimizer state, the gradient, but also the weight. Okay, so each parameter, each server no longer have the whole copy, the entire copy of the weight. It only have 1 over n of the weight. So the weight is also sharded, splitted, partitioned across n GPUs. So the total number of total number of bytes per node becomes 0.25 bytes. For 80 gigabyte of memory, you can now fit 320 billion parameters. So that's a lot larger. So this is the widely used approach to train these large language models. Okay, so we shard the weight, shard the optimizer state, shard the gradient, and also shard the weight across the GPUs. So we can increase the trainable parameter from just maybe 5 billion parameters all the way to 300 billion parameters. Okay, so in PyTorch, this 0.3 is an algorithm proposed by Microsoft. It's implemented by fully sharded data parallel. Okay, it's known as FSDP, very widely used library these days. Feel free to try it out. So for large language models below like 70 billion parameter, it's pretty safe to use this approach to train it. Okay, so that's the 0 and FSDP. Now let's switch gear to talk about pipeline parallelism. Okay, remember we have 4 parallelism to talk about. One is data parallelism, including communication primitives and sharding, and pipeline parallelism, tensor parallelism, and sequence parallelism. Now let's switch gear to talk about second part, which is pipeline parallelism. So for data parallelism, what are we splitting? We're splitting the data, sharing the weight. Now we are splitting the data. Instead of splitting the data, we want to split the model. Okay, so the model may have many layers. We can put each layer on one worker. What is the good thing about large language model is that different blocks, different layers are identical. Identical number of hidden size, identical number of heads. So each parallel pipeline stage are taking exactly the same time. So which is very suitable for pipeline parallelism. if we split this 350 gigabyte across 8 cards, so each card require only 43.75 gigabytes, which is smaller than 8 gigabytes. So this is the memory required for the 175 billion parameters of weights. So that's another dimension to fit a larger model across within the limited GPU memory. So a naive implementation basically partition the training data flow. Say we have 4 different layers, and forward F0, 1, 2, 3, and backward 3, 2, 1, 0. Okay, we need to store the intermediate activations to calculate the backward. And so this is the forward, GPU 0, 1, 2, 3, and backward 3, 2, 1, 0. Finally, we can update. So the model is split into 4 partitions in this way, and assigning each partition to 1 GPU. And the problem is that if we just process a single batch in this way, GPUs are underutilized. A lot of idle, a lot of bubbles in this case. So what is the theoretical utilization here? So only 1/4, 25% utilization, because most of the time the GPU is idle. So what is the best way to do that? Say previously we have a big batch, now we want to scale it with micro batch pipeline parallelism. What it's saying is that previously we have like 16 batches, now we want to split it into 4 such 4 batches. So rather than naive parallelization, now we can make it look like this. So small batch 1, 2, 3, 4 batches, and then after GPU 0 completes F00, it can handle the data to GPU 1 to compute F10, and the GPU 0 continue to compute F01. Okay, so in this way, the bubble is a lot less compared with the naive implementation. So we want to make the computation split it more fine-grained in a fine-grained manner. Previously, 25% utilization. Now using micro batch, it can improve it to 57%, which is 2.5x improvement. So the lesson we learn here is that we want to split the training in a fine-grained manner. So beyond the pipeline parallelism to split the model, we also have another degree to split the model, which is tensor parallelism to split the model. Okay, to further improve the granularity, to make it more fine-grained by further partitioning the model, not just the layer. Even for a single layer, we want to continue partitioning that. Say a layer has a 2 by 3 matrix. Okay, so we want to, this is the single FC layer, right? A single FC layer. We want to partition that into 3 parts. GPU1, GPU2, GPU3. And each GPU is calculating only 1/3 of the matrix. And finally, we can get the result in parallel. So partition the model in a more fine-grained manner within a layer. And that fits perfectly for large language model. So this is the illustration of tensor parallelism in Megatron. So including both the MLP layer and also the self-attention layer. Here we want to minimize, what do we want to minimize? Minimize the communication, right? Since compute is cheap, communication is expensive. So we only need to communicate in F and G in the start, in the end, which denotes this all reduce and synchronization operations. Okay, so this is, one is scatter, one is the all reduce operation. And similarly, communication only happens in the beginning and also in the end. And let's see how that works. First, for the FFN layer. So we have 2 FFN layers in large language model. Okay, 1 FFN layer, a second FFN layer. We just give an example. to be simple, 1 by 2 matrix. This is the activation, 1 by 2, and 2 by 6, which is the weight of the first FFN layer. And we have 2 GPUs in this case. We split it in this way. Each GPU hold 2 by 3 and 2 by 3. Two GPUs, that's 2 by 6, right? So we first do a broadcast, okay? Broadcast the activation to 2 GPUs, GPU 1, GPU 2. We perform half of the matrix multiplication on each GPU, the other half on the second GPU, and we get Y1 and Y2, okay? Corresponding to here are Y1 and Y2. No communication is needed here, and then we can directly move to the next section. In the next section, we are performing the second matrix multiplication, okay, which is of dimension 6 by 2. Okay, so this is the activation from the previous layer, and we have the matrix 6 by 2, so 6 by 2, right? Now we split it horizontally. GPU 1, GPU 2. GPU 1 is responsible for the first half. GPU 2 is responsible for the second half. And what we do here is we perform Y1 times B1 independently with Y2 times B2. Okay, Y1 times B1, Y2 times B2. Okay, so no communication is needed because Y1 is associated with B1. There's nothing to do with B2, right? And then we can obtain 2 intermediate outputs. Z1, which is 1 by 2, Z2 is 1 by 2. What is the final dimension of the matrix multiplication? 1 by 2, 2 by 6, 6 by 2. So the result should be 1 by 2, right? But now we get 2 1 by 2 tensors. So they are partial sums. So we have to sum up the partial sum. And now we have to do a communication. We want to do all reduce operation to sum them up to get a Z. Okay, so corresponding to here, we do all reduce operation to sum them up into Z. So we only need a broadcast in the beginning and all reduce in the end. And in the middle, these 2 matrix multiplications are done in parallel across 2 GPUs, GPU 1 and GPU 2 in this case. So 2 matrix multiplications corresponding to the 2 FFN layer in large language model is perfectly parallelizable. And let's look at here in the middle of the MLP, we discussed that it doesn't require any communication, right? Because it takes the first matrix is partitioned vertically, the second is partitioned horizontally, and there's no communication is needed in the middle. And let's see, how do we do that for the attention layer? So this is the self-attention with QKV transformation, softmax, and then matrix multiplication, 2 matrix multiplications, finally followed by a output projection layer. Okay. So this is the QKV transformation matrix. Okay. We have QKVO. We have 4 transformation matrix. Okay. 3 for the input, 1 for the output. So this is the 3 transformation for the input. The hidden dimension is 2. Okay. So we have 2 by 6, 2 by 6 for Q, 2 by 6, but for K for the key, and 2 by 6 for the value. Okay. The input is 1 by 2. 1 by 2, 2 by 6. So that's perfect match. So what we do here, we also split vertically across 2 GPUs. So each GPU is responsible for only half of the hidden dimension. Actually, that's the head dimension. And each GPU is responsible for 1 head. It's 1 head, this is another head, and we do a broadcast. Okay, so X is broadcasted to GPU 1 and the GPU 2. And GPU 1 is holding the first half, the transformation matrix for Q. GPU 2 is responsible for the second half of the transformation matrix for the Q. Similar for the K and similar for the V. Okay, we are broadcasting X in this way. So we do the matrix multiplication, 1 by 2, 2 by 3, so we get 1 by 3, 1 by 3, corresponding to the QKB transformation. And next, we want to do the attention. Okay, so it's QK transpose times V. Okay, there's a softmax. So we do for the first GPU. Remember right here, the first GPU already has Q1, K1, V1. Second GPU has Q2, V2, and K2. Right. So we are doing them separately for Q1, K1, and V1. We can do the QK transpose softmax times V. Okay, so QK transpose softmax times V independently as the Q2. Okay, so QK transpose softmax times V, they are independent. And then we get Y1 and Y2. Corresponding to here, we get Y1 and Y2. So far, no communication is needed. And finally, we want to do the output projection. Remember, we have Q, K, V, O, 4 projection matrices. Now we are talking about the last output projection. We have Y1 and Y2 right here. And this is the projection matrix, which is 6 by 2. Input is 1 by 6. So we split the output projection horizontally, such that we can do the B1 with the first half and B2 with the second half. So Y1 is multiplied with B1, Y2 is multiplied with B2, and similar to before, we get these two intermediate outputs, Z1 and Z2. And finally, we do all reduce. Now we need this operation, this all reduce operation. We need this communication right here. We do a communication in the last end to get a Z, final Z. Okay, so that's the whole process of splitting in the head dimension for calculating the attention. And the beauty here is that we only need communication, a broadcast in the beginning, and the communication which is all reduced in the end, right here in G in green, and everything in the middle. There's no communication needed across the two GPUs, which is why this attention mechanism fits perfectly for multiple GPUs. And it's so easy to scale it up. And Megatron actually made a huge contribution to scaling up this large language model training across multiple GPUs. I don't know if the designer of Transformer actually thought about this parallelization process, but it's very beautiful that no communication is needed in the middle for both the attention and also for the two FFN layers. But this is a perfect example for algorithm and system co-design for neural network acceleration. All right, we are 3 quarters in our journey. Okay, we talk about data parallelism, by parallelizing the data, sharing the model. We also talk about pipeline parallelism and tensor parallelism, which is sharing the data and partitioning the model. Now let's talk about the last one, the last parallelization technique, which is sequence parallelism. This part of the lecture is new this year. Don't have that yet in the last year, because this is a very trending topic for handling long context. Long context is very crucial. For example, for natural language processing, you want to understand long documents, right? Long documents, many books, complicated financial report, legal documents, etc. Long context is also important for video understanding. You want to understand the history, to know when and what is happening at what time. It's also important for robotics. You want to have a long trajectory of what has happened in the past in order to predict what's going to happen in the future. So all that require a lot of tokens, and tokens are very valuable. This context length is also valuable, but it's very complicated to train, take a lot of GPU memory. That's why we need sequence parallelism to partition this long sequence, this long context into multiple GPUs. So one GPU can handle only a limited amount of tokens. Again, the rule of thumb is we want to minimize the communication, maximize the utilization. And let's see how can we partition that. So this is the basic concept. Say we have a book of 3 chapters, Maybe each chapter is say 10K tokens. Now we have 30K tokens. We put 10K for each GPU. They are sharing the same weight, same model, but different part of the sequence, different part of the data. The question here is that each GPU only has its own piece of data, right? For the query, GPU1 has the first part, GPU2 has the second part, GPU3 has the third part. Similarly for the key and the values, right? So different GPU only has its own QKV. However, for the attention mechanism, we need to attend the first part of the document with the second part, first part with the third part, second part with the second part, second part with the third part, the third part with the third part, right? So that's a n by n matrix, which require a lot of communication. You cannot just do the attention locally. If you just, without any communication between GPU 1, 2, 3, what's going to happen? Everything can only attend locally. This chapter 1 will not see chapter 2. Chapter 3 will not be able to see chapter 2. Okay, so you cannot mingle the data anymore. Say you want to correlate something happened in chapter 2 with chapter 3, you cannot do that. Only chapter 3 with chapter 3, chapter 2 with chapter 2, chapter 1 with chapter 1. That's too bad. Let's see how do we solve this problem. Okay, I'm going to introduce two methods. Feel free to come up with third one in your final project. But solution one is a popular technique called deep speed analysis, which is very widely used technique these days to repartition the data in the attention layer. So how do we do that? Let's see. So this is a QKV transformation matrix. So we have the 3 tokens. Just use that as example. 1, 2, 3, and we feed the token 1 to GPU 1. Okay, so token 1 is 1 by 2. Transformation matrix is 2 by 3. So the result will be 1 by 3. Okay, 1 by 3 for the Q, 1 by 3 for the K, 1 by 3 for the V. Okay, so GPU2 is responsible for the second part of the token. Okay, second part of the token, the background is in green. Okay, background is in green. And the third GPU is responsible for the third part of the token. Okay, the background is in yellow. And GPU 1, 2, 3 all share the same QKV transformation matrix. So by multiplying this 2 by 3 matrix with the 1 by 2 by 2 by 3, we get 1 by 3 for the Q and for key and for V. Okay, so far so good. We are each GPU is responsible for only 1/3 of the tokens. Okay, 1/3 of the tokens in different color. And now we want to do the attention. Attention requires the first token, first part of the token also attend to the second part attend to the third part. So how do we do that? We want to do all-to-all communication right here. Okay, so for all the queries, all the queries as previously in GPU1 are GPU2 and GPU3 for the different heads, right? We have 3 heads in this case. We have the light green, we have dark green, and we have green, right? So now we want to collect everything related to the dark green into the third GPU, everything related to the light green in the second GPU, everything in the, we call it normal green in the first GPU, right? So each GPU is responsible for one part of the head. Now we are partitioning in the head dimension. Previously, we are partitioning in the sequence dimension. Okay, along sequence, different part in blue, in green, in yellow, right? Now we are partitioning the head dimension. This is head 1, head 2, head 3 in green, light green, and dark green, right? Now we partition the head in the head dimension. So GPU1 is responsible for head 1, everything related to green. So we just collect everything in the first column, which is the first head, collect everything to GPU1, so that we can compute the QKV, the attention, the complete attention for all the sequence, right? So it contains from token 1 contains from token 2 contains information from token 3, right? So everything related to the first head, the entire sequence, now is in GPU1. Everything related to the second head for the entire sequence now is in GPU2. Everything in the third head for the entire sequence now is in GPU3. Okay, so we do the attention computation separately. So this way, you can see where does the communication happen. Communication happens here, right? We need to do all-to-all communication. Okay, so previously each GPU has green, light green, dark green. Now GPU1 has everything related to green. GPU2 everything related to light green. GPU3 everything related to dark green. So the number of GPUs equal to the number of partition in the sequences, and we chop the sequence into 3 parts. We have 3 GPUs, and also equal to the number of heads. In this example, we have 3 heads. So what's the limitation of this approach? Because you have to first calculate the QKV transformation. You have to calculate this matrix multiplication before calculating the QKV transformation. And therefore, in the middle, you have to do a communication to exchange the data. So everything related to head 1 is gathered in GPU1. That's exactly the case. This is GPU1 only has head 1. GPU2 only has everything in head 2. But you cannot have that here because here we are partitioning the sequence on different GPUs. And not here, GPU1 has all the heads, but only related to the first third of the sequence length, only first third. So that's why we need such shuffle. Yeah. Right, exactly. Right. Yes, that's the answer to why was the limitation here, right? The all-to-all communication is pretty heavy right here. Within the node, that's pretty good. NVIDIA has NVLink. Across the node, we have NVSwitch, but communication in general is very expensive. And the other limitation is actually what is the max amount of parallelism we can have. For sequence, you can have a limited amount of segments, but for the heads, you have a limited amount of heads. 32 heads, 16 heads, 8 heads, that's the limitation you can have. The max amount of parallelism you have is limited by the number of attention heads in the model, which is a fixed number after the model is trained. So that's the Ulysses approach. And let me introduce the second solution, which is also quite popular, called the ring attention. In Google's paper, they mentioned this. The Berkeley paper also mentioned this. It's a pretty powerful approach. So we want to communicate such that the GPU1 sequence can also attend to GPU2. GPU1 also want to see GPU3, right? So what does it remind you of? The ring or reduce, right? The ring or reduce. So you have a ring, GPU1, 2, 3, GPU1, 2, 3. Okay, form a circle right here. In the first cycle, okay, we just rotate it by 1/3, such that we can communicate between GPU1 and 2, such that we are no longer computing only the diagonal, but also attending between the first third and the second third of the document. Okay, so this is the first third of the document previously on GPU1. Now GPU1, GPU2 switched. And see here, previously it's 1, 2, 3. Now it's switched. It becomes 3, 1, 2. So the second third of the sequence now reside on GPU1. Okay, so still within GPU1, we are doing the attention, but now we are attending the blue document with the green one. Okay, the first third with the second third. In another cycle, okay, we rotated one more time, such that GPU1, the query will be multiplied with the orange document, the last third of the document. Okay, so we computed the attention in this corner. Okay, so we put it together. Previously, we only have the diagonal part, which the blue document attend to blue document. The first third attend to the first third. Now, the first third attend to the second third. And then the first third attend to the last third of the document. So now we complete the whole attention process. So previously, a lot of places are white, meaning the attention has not been computed. Now we fill in the white with color, meaning that we have computed. And in another cycle, we filled in everything and computed. So that's the ring attention, using ring attention to perform sequence parallelism. In this way, it's not limited by the number of heads as the max amount of parallelism we can have, but this can effectively increase the context length during training and inference. So one interesting part is recently we've been combining these two methods. One is the Ulysses method, the repetitioning in attention layers versus this ring attention into a 2D parallelism by combining them. Since within a node, 8 GPUs has higher bandwidth of communication bandwidth compared with between the node. So between the node, we can use ring attention. And within the node, we can use this Ulysses method. Okay, so in that way, we can effectively perform 2D parallelism by combining these two parallelism methods to utilize the heterogeneity between the node versus within a node. And that paper is called Long Villa. Feel free to check it out. It's also open sourced. All right, and let's move on. To summarize of today's lecture, we talked about data parallelism and sequence parallelism. They are both splitting the data. Okay, sequence parallelism is new due to this long context requirement for large language model. We also talk about pipeline parallelism, split the model by layer, and also tensor parallelism, split the model by tensor. We also talk about these communication primitives, the reduce, the all reduce operation, and also this magic ring all reduce, and this recursive halving all reduce using log n complexity. We also talk about 0, 1, 2, 3, and FSDP, which is probably the most popular technique for distributed training in PyTorch, and also how to implement pipeline parallelism and also tensor parallelism in the context of large language model. All right, that's all for today's lecture, and we will also release the grading for Lab 4. And for the final project, some of you asked about what is the template for the final project's final report and also the proposal. So we use the NeurIPS template, so very standard flagship machine learning conference. Basically, should include a proposal, should include the motivation. What kind of problem are you trying to solve? Why do you need to solve that problem? And also starting with the abstract, just a few lines, probably 10 to 20 lines, just abstract, like the abstract of the paper, and then starting with the motivation, and also what is your method, what is the prior methods, what is your method, and what is the final result, and how does your result compare with the prior art. That's roughly the template of the final report. And for the proposal, you can just remove the result section, and then that is the proposal. If you have any questions, feel free to come to our office hour, and we'd love to help you. Okay. All right, that's all for today's lecture. Thank you.